Hi, welcome back to my class in Mathematics in the Modern World. For today, we will complete the solution of the linear program we were solving in the last lesson. In the last lesson, we developed the second simplex tableau from the initial simplex tableau. And the initial simplex tableau was developed from the modified linear program. And today, we will complete the solution. This was the second simplex tableau that was developed in the last lesson. And we have seen that there was an improvement in the value of the objective function. And now we will see if we can still improve on the value of the objective function. The criteria for you to determine if you are done with the solution, if the solution is complete, is by inspection of the last row. The last row is C sub j minus Z sub j. If all the entries in the last row are 0 or negative, then you are done with the solution. That means you have reached the optimal solution, the best solution. Again, the criteria for you to determine if you are done with the solution, you are finished with the solution, or the solution is complete is by inspection of the entries of the last row. The last row is denoted by C sub j minus Z sub j. If all the entries in the last row are either negative or 0, then you are done with the solution. The solution is complete. But in this second tableau, you can see that there is still one positive entry in the last row. That means that we are not yet done with the solution. That means that there is still a third simplex tableau to develop. Now, in this second tableau, there is only one positive entry. And the positive entry is under the variable a, which means that the variable a is our entering variable. Again, entering variable is the decision variable with the most positive entry in the last row. And it is called entering variable because in the third simplex tableau, the decision variable a will enter the basis column. Now, if there are 2 or more positive entries in the last row, you will select the most or the highest, the biggest positive entry in the last row. If there are 2 or more positive entries in the last row, you will select the most positive, the largest, or the biggest positive entry in the last row. And the decision variable with the most positive entry or largest positive entry in the last row becomes your entering variable. But for the second tableau, there is only one positive entry, and that is 11 over 10, and 11 over 10 is under the decision variable a. Thus, a is the entering variable. As I said, it's called entering variable because in the third simplex tableau, the variable a will enter the basis column. But for the variable a to enter the basis column, one of the variables in the basis column in the second simplex tableau has to leave. Again, for a to enter the basis column, either the slack variable S1 or the decision variable B will leave this simplex tableau or will leave the basis column. Now we determine which of these two will leave the basis column. And we do that by dividing the entries of the last column or the S column or solution column by the corresponding entries of this column. This column containing the entering variable a is what we call, again, the pivot column. Pivot column, as I said in the last lesson, is the column containing the entering variable. and to determine the outgoing variable or the leaving variable, which can either be the first slack variable S1 or the decision variable B, we divide the entries of the last column or the S column or solution column by the corresponding entries in the pivot column. We divide 10 by its corresponding entry in the pivot column, 11 over 2. We divide 10, the first entry in the last column is 10. We divide that by the corresponding entry in the pivot column, 11 over 2. And to divide 10 by 11 over 2 is to multiply 10. This is equal to 10 multiplied by the reciprocal of 11 over 2, which is 2 over 11. And 10 multiplied by 2 is 20, divided by 11. And that's 1 point something. Next, the next entry in the last column is 7, and we divide 7 by the corresponding entry in the pivot column, 7 over 10. 7 divided by 7 over 10. Again, to divide 7 by 7 over 10 is to multiply 7 by the reciprocal of 7 over 10. To divide 7 by 7 over 10 is the same as multiplying 7 by the reciprocal of 7 over 10, which is 10 over 7. And 7 over 7 will cancel out because 7 over 7 is 1. And 1 multiplied by 10 is 10. I canceled out 7 over 7 because it's 1. Now, in selecting the outgoing variable or the leaving variable, we take the smallest positive quotient. The zero quotient, the negative quotient, and undefined or not defined are not included in the selection of outgoing or leaving variable. Again, in selecting the leaving variable or outgoing variable, we only consider the positive quotient. We do not consider the zero quotient, the undefined or not defined, and the negative quotient. Those are not included in the selection of the outgoing variable or leaving variable. Now, if there are two or more positive quotients, like in this case, both the quotients 20 over 11 and 10 are both positive, you select the smallest positive quotient. And between 20 over 11, which is 1 point something, and 10, the smaller is 20 over 11. And 20 over 11 is in the row of the first slack variable S1. That means the slack variable S1 is the leaving variable or outgoing variable. The first slack variable S1 is the leaving variable or outgoing variable because it will now leave the simplex W or the basis column, and S1 will be replaced by the entering variable, decision variable A in the third simplex W. So we now write S1 replaced by A, we write here A. And the decision variable B will remain in the basis column. The coefficient of A in the objective function is 6. And the coefficient of the decision variable B in the objective function is 7. Now we will determine the rest of the entries in the third simplex W. In developing the third simplex tableau, we are just repeating the steps and the process we went through when we developed the second simplex tableau from the initial simplex tableau. We are repeating the process until we get the optimal solution, which occurs when all the entries in the last row are either negative or zero. That is why this simplex method or simplex algorithm is known as an iterative method. You go through the same process again and again until you reach the best solution known as optimal solution. Next, we determine the pivot element. From last meeting, we said that pivot element is the element at the intersection of the pivot column and the pivot row. And is the pivot column, it is the column that contains the entering variable. And this is the pivot row. It is the row with the smallest positive quotient, or it is the row containing the outgoing variable or leaving variable. And you look at the entry at the intersection of the pivot column and the pivot row. And that element or entry is 11/2. (11/2) is called the pivot element. The pivot element is the element at the intersection of the pivot row and the pivot column. In the third simplex tableau, we must change the pivot element to 1 using this elementary row operation, the first of the 3 types of elementary row operations, where the entries of the old row are replaced by the scalar multiple of the entries of the old row. So the pivot element is to be changed or converted to 1, and the rest of the entries in the pivot column, except the last 2 entries and the first 2 entries, 6 and 8, and these last 2 entries, the rest of the entries in the pivot column, except the last 2 entries and the first 2 entries, and the pivot element are to be changed to 0. And that element to be changed to 0 is 7/10. So the pivot element that is to be changed to 0, I encircle that element, and that element to be changed to 0, I box that element. So for you to distinguish between the element to be changed to 1, that is the element with box, and the element to be changed to 0 is the element that is boxed, and the element to be changed to 1, the pivot element, is the one with encircled. We start with the pivot element. We will change this to 1 using this elementary row operation. R sub n denotes the new entries of the pivot row. R sub p denotes the entries, the old pivot row. And E here is the pivot element to be changed to 1. And the element to be changed to 1, the pivot element in the second simplex tableau, is 11/2. Now you perform this operation, the new entries of the pivot row, and again the reason we call this elementary row operation because we are operating on a row. We apply the operation on all the entries of the row, not just on a single element or number. The new entries of the pivot row is obtained by multiplying the old entries of the pivot row by the reciprocal of the pivot element. Our pivot element is 11/2, and 1/e is the reciprocal of 11 over 2, which is 2 over 11. And this reciprocal of the pivot element, we multiply by the old entries of the pivot row, which are 11 over 2, 0, 1, negative 1 over 2, and 10. 2 over 11 multiplied by the old entries of the pivot row. We have 11 over 2, 0, 1. And negative 1 half, 10. We multiply each of these entries of the old pivot row by 2 over 11. 2 over 11 multiplied by 11 over 2 is 1. 11 over 11 is 1. 2 over 2 is 1. So 2 over 11 multiplied by 11 over 2 is 1. 2 over 11 multiplied by 0 is 0. 2 over 11 multiplied by 1 is 2 over 11. Now 2 over 11 multiplied by negative 1 half. The 2 in the numerator and 2 in the denominator will cancel out because it's 1. And you get this positive multiplied by negative is negative 1 over 11. 2 over 2 are cancelled. So 2 over 11 multiplied by negative 1 half is negative 1 over 11. And 2 over 11 multiplied by 10, multiply 2 by 10, that's 20 over 11. And these are the new entries of the pivot row. And we will write this in the row of the outgoing variable, which is now replaced by the entering variable A. This is our old pivot row, and this is now our new pivot row with the new entries 1, 0, 2 over 11. Negative 1 over 11 and 20 over 11. Next, we change this entry to 0 using the second type of elementary operation given by the following. The new entries of the ith row. Now, because we have to change this to 0, if we have to change 7 over 10 to 0, we have to change all the entries of this row. Not only 7 over 10 is to be changed to 0, we must change all the entries of this row if we want to change 7 over 10 to 0. And we change 7 over 10 to 0 using this second type of elementary operation, where r sub I is the row containing the element or entry to be changed to 0. In this example, r sub I is the second row. We start counting the row after the variable row. This is called the variable row because it is the row that contains the variables, the decision variables and the slack variables. So this is the decision row. And after the decision row, you have row 1, row 2. And we have to change all the entries of this row, which is row 2, R2. The new entries of row 2 are obtained by multiplying the new entries of the pivot row by the negative of the element to be changed to 0. A here is the element to be changed to 0. And in this example, the element to be changed to 0 is 7 over 10. And that is our A. And we take its negative, multiply 7 over 10 by negative. Multiply by the new entries of the pivot row. The entries of the new entries of the pivot row, 1, 0, 2 over 11. Negative 1 over 11 and 20 over 11. And to these products, we add plus r sub I. We add the entries, the old entries of the second row. The row whose entries are to be changed. 7 over 10, this is your second row. 7 over 10, 1, 0, 1 over 10, and 7. 7 over 10. Plus 7 over 10. Plus the old entries of the row whose entries are to be changed. In our example, r sub I is row 2. And the old entries of row 2 are 7 over 10, 1, 0, 1 over 10, and 7. First, you multiply these entries by negative 7 over 10. Negative 7 over 10 multiplied by 1 is negative 7 over 10. Negative 7 over 10 multiplied by 0 is 0. Again, negative 7 over 10 multiplied by 0 is 0. Negative 7 over 10 times positive 2 over 11. That's negative 14 over 110. Negative 7 times 2 is negative 14. Over 10 times 11 is 110. Now, I said that when solving the linear program by Simplex method, we will not use decimal numbers, but instead we will use fractions in lowest terms. Now, this negative 14 over 110 can still be reduced to lowest terms by dividing 14 and 110 by the greatest common factor. And the greatest common factor is 2. Negative 14 is divisible by 2. 110 we can divide by 2. Or if you want, 2 over 10 can be reduced to lowest terms by dividing 2 by 2 and dividing 10 by 2. So 2 will cancel out and this will become 7 over 5. And you have negative 7 times 1 is negative 7. That's the same as dividing negative 14 by 2, negative 7. And if you divide 110 by 2, you will get 55. And that is the same as multiplying 11 by 5. If you reduce 2 over 10 to lowest terms, which is 1 over 5, so this will become 7 over 5, and you have 5 times 11 is 55. Just remember that if the fraction can be reduced to lowest terms, you reduce it to lowest terms. Now, negative 7 over 10 times negative 1 over 11. Negative times negative is positive. 7 times 1 is 7. Over 10 over 10 multiplied by 11. You get positive 7 over 110. And finally, we have negative 2 over 10 multiplied by 20 over 11. Now, 20 is divisible by 10. So, you divide 20 by 10, that's 2. Multiplied by negative 7 is negative 14 over 11. Again, negative 7 over 10 multiplied by 20 over 11. 20 divided by 10 is 2. Multiplied by negative 7 is negative 14, and the denominator is 11. And to these products, we add 7 over 10, 1, 0, 1 over 10, and 7. We now perform the addition. Negative 7 over 10 plus positive, plus positive 7 over 10 is 0. And 0 plus 1 is 1. Negative 7 over 55 plus 0 is negative 7 over 55. And 7 over 110 plus 1 over 10, you have 7 over 110 plus 1 over 10. Now, if you have a scientific calculator, most scientific calculator can perform additions of fractions. You use your calculator, but you can add this mentally. We want a common denominator. So, you multiply 1 over 10 by 11 over 11. And 10 multiplied by 11 is 110. So, denominator here is 110, and here denominator is 110. Common denominator is 110. In the numerator, we have 7 plus 1 multiplied by 11. 1 multiplied by 11 is 11 plus 7 is 18. Again, this fraction can still be reduced to lowest terms because 18 and 110 are both divisible, can be divided by 2. So we divide 18 by 2. 18 divided by 2 is 9. And 110 divided by 2 is 55. Thus, 7 over 110 plus 1 over 10 is 9 over 55. And finally, we add negative 14 over 11 plus 7. Negative 14 over 11 plus 7. For 7 to have a denominator of 11, you multiply 7 by 11 over 11. Now, the common denominator is 11. We find the numerator. 7 multiplied by 11 is 77. And 77 minus 14. And 77 minus 14 is 63 over 11. Thus, negative 14 over 11 plus 7 is 63 over 11. And these are the new entries of this row in the third simplex tableau. 0, 1, second row. These are the new entries of the second row. This is the first row. After the decision variable, you start counting 1, row 1, row 2. And the new entries of row 2 are 0, 1, negative 7 over 55. Nine over 55. And 63 over 11. Now, it's easier to find the elements or entries of the last two rows. The entries of Z sub j row are obtained again by multiplying the entries of each variable column by the corresponding entries of C sub j column. We start with the entry here, 6 multiplied by 1 plus 7 multiplied by 0. 6 multiplied by 1 is 6 plus 7 multiplied by 0 is 0. Hence, we have 6 plus 0 is 6. Next, the entries of the second variable column, column B, 6 multiplied by 0 plus 7 multiplied by 1. 6 multiplied by 0 is 0, plus 7 multiplied by 1 is 7. Thus, we have 0 plus 7 is 7. The next variable column, the S1 column, we multiply the entries of S1 column by the corresponding entries in C sub j column. We have 6 multiplied by 2 over 11 is 12 over 11. That 6 multiplied by 2 is 12 over 11. And to 12 over 11, we add 7 multiplied by negative 7 is 49 over 55. 7 times negative 7 over 55 is negative 49 over 55. Now, for us to have a common denominator of 55, we multiply 12 over 11 by 5 over 5. As I have told you, if you have a scientific calculator that can perform addition of fractions, you do the computations using your scientific calculator. But you have an option to compute this manually. So we multiply 5 multiplied by, now the common denominator is 55, denominator here is 55, 5 times 11 is 55. And we find the numerator, 5 times 12 is 60, 60 minus 49 is 11. Again, 5 times 12 is 60. 60 minus 49 is 11. And common denominator is 55. The next entry here is obtained by multiplying the entries of this S2 column by the corresponding entries of C sub j column. We multiply 6 by negative 1 over 11, we get negative 6 over 11. Plus 7 multiplied by 9 over 55. 7 multiplied by 9 is 63 over 55. Plus 63 over 55. Again, for us to have a common denominator of 55, we multiply negative 6 and 11 by 5 over 5. And the common denominator now is 55. We have 55 in the denominator. And 5 times 11 is 55. Now we find the numerator. 5 times negative 6 is negative 30 plus 63, or 63 minus 30 is 33. And 33 over 55 can still be reduced to lowest terms by dividing 33 by 11. 33 divided by 11 is 3. And 55 divided by 11 is 55. Again, 33 divided by 11 is 3. 55 divided by 11 is 5. Hence, 33 over 55 in lowest terms is 3 over 5. But this 11 over 55 can also be reduced to lowest terms. Let us reduce this to lowest terms by dividing 11 and 55 by 11. 11 divided by 11 is 1. And 55 divided by 11 is 5. So instead of writing 11 over 55, we write this in lowest terms, which is 1 over 1 over 5. And the entry here is 3 over 5. The last entry we have to find is the entry in this cell, obtained by multiplying the entries of the last column or solution column by the corresponding entries of C sub j. We multiply 6 multiplied by 20 over 11. Multiplying 6 by 20, that's 120 over 11. Plus, always multiply and add the products. Plus 7 multiplied by 63 over 11. Multiply 63 by 7. 63 multiplied by 7. There, 63 multiplied by 7. 7 times 3 is 21. Carry 2, 7 times 6 is 42, plus 2 is 44. Sorry, 44. The 63 multiplied by 7 is 441. We have 7 times 63 is 441. Denominator is 11. Now we have a common denominator of 11. And we simply add the numerators of these two fractions. 120 plus 441 is 561. 120 plus 441 is 561. Common denominator is 11. Now we find the entries of the last row. Those are the difference of C sub j, which is this top row, minus C sub j, which is the second to the last row. So we have 6 minus 6 is 0. 7 minus 7 is 0. And 0 minus 1 over 5 is negative 1 over 5. And 0 minus 3 over 5 is negative 3 over 5. Now, you look at the last row. All the entries in the last row are either 0 or negative. There is no more positive entry in the last row. The entries in the last row are either 0 or negative. And that means that we are done with the solution. Our solution is now complete, and we have obtained the optimal solution or the best solution. Now we will write the optimal solution, which is the solution corresponding to the third simplex W. We now write the solution corresponding for the third simplex W. Since in the third simplex W, all the entries in the last row are either 0 or negative, that means that we are done with the solution, or the solution is complete. And so instead of writing third solution, the solution corresponding to the third simplex W, we write optimal solution. In the second simplex W, we write the solution corresponding to the second simplex W as second solution, because we are not yet done with the solution, or the solution is not yet complete after the second simplex W, because as we have seen, there is still one positive entry in the last row of the second simplex W. So we write the solution corresponding to the second simplex W as second solution. But for the third simplex W, all the entries in the last row are either positive or negative, or there is no more positive entry in the last row, which is an indication that the solution is complete. And when the solution is complete, instead of writing third solution corresponding to the third simplex W, we write optimal solution. Optimal solution means best solution. You can see that from the initial simplex W to the third simplex W, we have three solutions. One solution corresponding to each simplex W. But among these three solutions, the third solution corresponding to the simplex W is the best solution, and we write that solution as optimal solution. And the variables that appear in the optimal solution are the variables you find in the basis column. In the basis column, we have A, and the value of A in the optimal solution is the corresponding entry in the last column, or the S column or solution column. That is why I denoted the last column by S for solution, because the values of the variables that appear in the basis column are the corresponding entries in the last column. These are the values of the variables in the solution. Hence, the value of A is 20 over 11. A is 20 over 11. The second variable in the basis column is B, and the value of B is the corresponding entry in the last column or solution column, which is 63 over 11. Thus, B is equal to 63 over 11. B equals 63 over 11. And as in the initial simplex W, and as the same with the second simplex W, if a variable does not appear in the basis column, it means that the value of that variable is 0. Now, the slack variables S1 and S2 do not appear in the basis column. That means their values are 0. S1 equals 0 and S2 equals 0. And the same with the initial simplex W and the second simplex W. The value of the objective function, or P, is given by the last entry in the last column. This is the last column, and the last entry in the last column is the maximum value of the objective function. So the highest or the biggest maximum value of the objective function P is 51 over 561 over 11. This is the highest value of P that you can obtain when A is 20 over 11 and B equals 63 over 11. Now, for your practice, please try to solve the following linear program by Simplex method or Simplex algorithm. Maximize P equals 5x plus 3y. Maximize P, you want to find the maximum value of P. That's the objective function given by 5x plus 3y. The decision variables are x and y, but you find the values of x and y that will give the maximum value of P subject to the following constraints. 2x plus 3y less than equal to 6, that's the first explicit constraint. 5x plus 2y less than equal to 10, that's the second explicit constraint. And x greater than equal to 0, y greater than equal to 0, the last two constraints are also known as implicit constraints or non-negativity constraints. They require that the values of the decision variables must be positive or 0. And you can see in the optimal solution of the problem we have just solved, all the values of the variables are either positive or 0 because of the implicit constraint or non-negativity constraints. Now, for this problem that you will solve by Simplex method, there are 3 Simplex tableaus. The initial Simplex tableau based from the modified linear program, and there is a second Simplex tableau, and the last is the third Simplex tableau from where you will get the optimal solution. And for you to be able to check your answer, I give you the final solution or the optimal solution for this linear program. What you will have to do is to show the complete solutions and the third simplex and the 3 simplex tableaus. For the optimal solution, the value of the decision variable x is 18 over 11. The value of the decision variable y is 10 over 11. And the slack variables s1 and s2 are 0. And the maximum value of p is 120 over 11. You can actually check if the maximum value of p is 120 over 11 by substituting 18 over 11 in the objective function. 5 multiplied by 18 over 11 plus 3 multiplied by y, 10 over 11. And you should get 120 over 11. 5 times 18 is 90 plus 3 times 10 is 30. 90 plus 30 is 120. And common denominator is 11. And that completes our first example for using Simplex algorithm or Simplex method for solving a linear program that contains explicit constraints, that contains less than equal to inequality, less than or equal to inequality signs. If you have question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure, or you may ask your friends and classmates to also subscribe to my YouTube channel, Art Kalison, so they may learn as well. Thank you for joining me in my class today.